Now that we have learned about spin, we can begin to study some applications of spin and also, of course, study some phenomena that occur in real life. So the first thing that we will look into is what happens if we take an electron and place it in a uniform magnetic field. Now this will give rise to a phenomenon that is called the Larmor precession that we'll take a look in just a minute. So what happens if we put an electron in this magnetic field? Well, there's going to be an interaction that is due to the spin of the electron. This interaction happens because the spin of the electron, this intrinsic kind of movement of charge, it's not an actual movement, but that's kind of the analogy that we many times use. What happens is that this electron is going to have this magnetic dipole moment that is caused by its spin, and it is proportional to it by a ratio that is called the gyromagnetic ratio. Gyromagnetic ratio. Now, why is this formula true? For now, we would just have to take it as an experimental fact, which is actually how it originated. And in order to explain it with theory, we need relativistic quantum mechanics, which of course is much more advanced than we are dealing with now. So I'm afraid that at least for the theoretical explanation, we are going to have to wait a little bit. And continuing, now what we have learned from electrodynamics and hopefully some sort of electromagnetic theory course that you may have had is that if we have a magnetic dipole moment, then this is going to give us a term in the Hamiltonian. This will give rise to energy. So, and this is given by the formula minus mu, the magnetic dipole moment, dot product with the magnetic field. So this is what we need to know about this interaction. Some part of this is just known experimentally. The other part is something that I hope you have seen in the electromagnetism courses. And now we have to take a look at this term. So let's give ourselves some examples. So let's say we have some magnetic field that is constant in some direction. Let's just choose z direction because that's what we usually choose, but it doesn't really matter. So in this direction, now what happens to this dot product? So we have the Hamiltonian, which is going to be minus mu, but mu is gamma times the spin, dot product with the magnetic field, which is B0 in the z direction. Now, what is this spin vector? This spin vector was h bar over 2 times a vector which each of the Pauli matrices. So it was sigma x in the x direction, sigma y in the y direction, sigma z in the z direction. So if we do this dot product, the only terms that are going to survive, it's going to be the h bar over 2, of course, and the sigma z. Whoops, it was supposed to be B0. So this is our Hamiltonian, minus gamma h bar over 2 sigma z B0. And now we would like to know, well, what exactly happens here? What is the energy? What are the expectation values of the spin, for example? What's going on? So let's begin, for example, by measuring the energy. So the energy, we know, is the eigenvalue of the Hamiltonian. So if the Hamiltonian operator acts on some state, we are going to get the value of the energy. So actually, let's do that. But of course, instead of any psi, this is going to be our particular states here. So what are the states? Well, we know that since the only two possibilities for spin are up or down, then the most general state that we can have is a linear superposition of both of these possibilities. So first we have some probability A plus some probability B, and both of them multiplying. This is the up spinner, this is the down spinner, and of course A squared plus B squared has to be equal to 1, since it either has to be up or down. There is no other possibility. Okay, so let's now, and this of course you can write in ket notation. So let's now let the Hamiltonian act on this. So what exactly was the Hamiltonian? It was this right here. So the Hamiltonian is now going to act on this state. So this is acting on the state. Now, what exactly was sigma z? Sigma z, this was a matrix. 1, 0, 0, minus 1. If you don't know where this comes from, then you might want to go back and take a look at the video where I explain where the Pauling matrices come from. Okay, so now we have this right here. Let's write the explicit form for the state. Now this is of course A times the up state plus B times the down state. And here with this product, we are going to get, in theory, we could do it separately for the up state or the down state. I'm going to do them both at the same time, just for the sake of time. So I'm going to get minus gamma h bar over 2 B0 factor of, and this is of course the up spinor, so this is going to be 1, 0, and this one right here is going to be 0, 1. So now we're going to do the product of these matrices. So we have A times 1 times 1, 0, 0, 0, 0. So this is going to be, once again, 1, 0. And then when this matrix acts on this right here, we're going to get minus B, 0, 1, because 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0, minus 1 times 1 is minus 1, so this is negative 1, but we can take the minus sign outside. So now we can actually see that what we get is minus gamma h bar over 2 B0 times A times the up state, and then we have plus gamma h bar over 2 B0 times B times the down state. So we can see that the eigenvalues of the Hamiltonian operator, since these right here, this is simply our states, it's going to be what is right next to it. So the energy, thinking about, I need more space, but I don't want to go to the next page, so I will delete this. Okay, so this right here, this is going to be the energy for the up state, and this right here is going to be the energy for the down state. So this is going to be gamma h bar over 2 B0, and the energy for the up state is going to be minus gamma h bar over 2 B0. So those are the values for the energy. Of course, if there's no magnetic field, then there's not going to be any energy. That makes sense, of course. So at least that makes sense. Now, what we would like to do is just take a look at the states that we're going to have. Now, since of course the Hamiltonian is time independent, the magnetic field is constant in time, it's not changing, we can use what we have already learned about the Schrödinger equation, and we can solve it by separation of variables. So we're going to get the same equation that we have seen for the Schrödinger equation, but this time for our spin state. So once again, the derivative with respect to time, this is going to be the same as the energy acting on the state. So here we can now apply separation of variables to this equation. So let's leave everything related to the state to the left, everything else to the right. So h bar, whoops, that's dividing. So dt h bar, and we're going to be dividing by I, but of course we can multiply and divide by I, so we can write it as minus I up here. And now we just integrate this, so we get that the natural log of this state is going to be minus I t over h bar. And now we can exponentiate all of this. Oh, I left the energy out. And this is of course going to be true for the plus or minus case. So now when we exponentiate this, we get that our time-dependent function is going to be some constant times e to the minus I, because this of course has some constant, which is then going to be added up to this constant right here when we exponentiate. So e to the minus I t e plus or minus divided by h bar. And the thing is that now we want to combine the time dependence with the time independent solution that we saw before, because before, of course, we saw that these states were some linear combination between the up and the down states. So now we want to combine these two. So let's add the time dependence in here. So here we're going to get this times big A e minus I, let me write it like this, e, but the positive energy here, t divided by h bar. And similarly here, a e minus I t e minus divided by h bar. But take into consideration, we already have one constant. These are two constants, random constants. So we don't need to write both of them. We can just absorb one into the other. Okay. So this right here is the most general solution for our spin states with the time dependence included. So let us now just go ahead and begin to look for some of the expectation values. So for example, we can look for the expectation values of the spin in the x direction. What is that going to be? Well, this is simply going to be our states. We take the Hermitian adjoint, and then we apply the operator, and then our state once again. And if you prefer, you can write it in bra and ket notation. This is the same. Just to make sure that everything is clear, let us write these ket, the bra and the ket explicitly. So let's begin with the ket. This is going to be what we have right here, but let us write the spinors in their actual form. So a times 1, 0, e to the minus I e plus t divided by h bar plus b 0, 1, e minus I t e minus divided by h bar. But what are these energies? Now remember, these energies, e plus minus, were minus plus gamma b0 h bar divided by 2. So these exponentials, now obviously it depends which one, because one is e plus and e minus. I'm going to do one, and the other one will simply have a different sign, as you will see. So this first exponential is going to be e to the I t h bar times, since this is e plus, it's going to be minus gamma b0 h bar divided by 2. So the h bars will cancel out, and we will be left with, I had a minus sign here, by the way. It's going to be minus minus, so plus I gamma b0 t divided by 2. And in the other case, since it doesn't have a minus here, this minus sign will continue to be there. So that's the only difference there. So this first exponential is going to be I gamma b0 t divided by 2. And this second exponential is going to be minus I gamma b0 t divided by 2. Okay, so these are the states more explicitly, but we can actually combine everything together into just one vector. So just multiply all of these constants in here, and just, well, maybe not constant because it depends on time, but just multiply everything into the vectors and then add the vectors together. So we get a ei gamma b0 t divided by 2, b e minus I gamma b0 t divided by 2. And we can from here, of course, find the bra, just taking the Hermitian adjoint of what we have here, which is going to be a e to the minus I gamma b0 t divided by 2, and b, this is of course now a row vector, so it's going to be b e I gamma b0 t divided by 2. So now we have the bra and the ket. So we can use this to immediately calculate now the expectation values. Let's do that in the next page. I'm actually missing the b0 there. Okay, so to calculate the expectation value, let's take the bra, copy it right here, and we now have to put the operator for Sx, which is h bar divided by 2, 0, 1, 1, 0. Once again, if you don't know where that came from, you should go back a few videos where I explain it. And then we have the ket, which is this part right here. So let's begin doing this product. So the first part, of course, will remain the same, and here we'll get 0 times the first one, 1 times the second. So the new vector will have this right here, and in the second position, it will be 1 times this, 0 times this. So basically, the new vector will flip these two quantities. Like this. So now we have to do this multiplication right here. So we have this quantity times this plus this times this. So let's see, we have h bar divided by 2 times a times b times the exponentials. But take a look at this, the exponentials are the same. So we're going to get twice the exponent. So the divided by 2 is going to go away. And then for the second one, we get plus ab, well, or ba, doesn't matter, and ei gamma b0 t. Once again, the divided by 2 goes away because we have twice the exponent, so the divided by 2 cancels out. So here we can actually factor out a and b, and we get e minus I gamma b0 t plus e I gamma b0 t. So these exponentials look quite interesting because they have a very similar form except for that minus sign. And now you might remember what this is. If not, it's okay. What I would advise you to do is to remember Euler's formula. So let's just go ahead and apply it. So what it says is that this right here, let's go for each exponential. So this is simply the cosine of gamma b0 t, since it's an even function, so the minus sign goes away. And since sine is odd, we can put the minus sign outside, and we get minus I sine of gamma b0 t. And for the second one, we get plus cosine of gamma b0 t plus I sine of gamma b0 t. So here these signs cancel out and we are left with 2 times the cosine. So the 2 will cancel out this one right here. So we get h bar ab cosine of gamma b0 t. So this is the expectation value for x. Okay, let me put a red box because we will want to come back to it soon. Now let's go for the expectation value of y. So I'll actually come back to this page where we have all of the bras and kets written down. Wait, maybe I don't want to erase this, because all I want to change, in fact, is going to be, I actually do have to erase it, yes, I changed it before, so it's fine. Okay, so we now want to do the same thing that we just did, but now with the operator for sy, which is going to be, whoops, I didn't mean to change the color, h bar divided by 2 times now the Pauli matrix in the I direction, which is 0 minus I 0. And then we have to put in the ket. Okay. So once again, we do this product first. So in the part up here, we get 0 times the first one, but we get minus I times the second one. And for the second term, we get I times this. So once again, this is basically going to flip, but now we're going to have the addition. No, I'm bringing something along that I didn't want to bring. Just 1 second. Okay, so this first part will be down here, this will be up here, and this will have minus I, this will have I. Okay, so that's what happens when we take this product. So I can now get rid of this matrix. So now let's do the product between this part and this part. So we get h bar divided by 2 times minus a b times I. The exponentials are the same, so we get twice the exponential, so e minus I gamma b0 t plus I ab ei gamma b0 t divided by 2. Here, no, not divided by 2, that cancelled out. Okay, so now we have this. Let's go to the next page and work this expression a little bit. Okay, so what do we have right here? Well, we can factor out the AB, so we get AB h bar divided by 2. In fact, we can factor out the I as well. And then we have minus e to the minus I gamma b0 t plus EI gamma B0t. So just as we did before, let's now convert this to cosines and sines. AB h bar I divided by 2 cosine of gamma B0t minus I sine of gamma B0t, but actually this is multiplied by a minus sign, so the first one will be minus, the second one will be plus, and then we have plus cosine of gamma B0t plus I sine of gamma B0t. Okay, so this time it's going to be the cosines that cancel out, and we will be left with the same constant up front, but then we have 2 times I sine of gamma B0t. So here the 2's will cancel out, the i's will give us a minus sign, so we get minus AB h bar times the sine of gamma B0t. Okay, so there's now one more expectation value that we would like to calculate. I want to go back here, so let's go for it. And that's going to be, of course, the expectation value for Sx. So the expectation, Sz. So the expectation value for Sz is now going to be, of course, the bra. Now we apply the operator in the z direction, which we know is h bar over 2. And this was, 1, 0, 0, minus 1. And now the ket. Okay, so well, first of all, let's do the product just as before. So when we do this product, we get 1 times this, 0 times this, so this first part will be unchanged, but for the second one we will get a minus sign here. So now let's do the dot product between these two vectors. So we get a squared this time, a squared, and this time the exponentials, take a look at this, they cancel out, so no need to write it down. And then we have minus b squared, right? So just let me make sure, so a squared this, the exponentials cancel out, b squared, and the exponentials cancel out. Okay, so the result is indeed just a squared minus b squared h bar divided by 2. And this is, in fact, this doesn't depend on the values of, this doesn't depend on time like the other results did. So let me now go to a new page where I will put everything together. So for Sx, we found that was a b h bar divided by 2 times, I think it was the cosine of gamma b0 t. For Si, we found that it was minus a b h bar divided by 2. Oh, actually this was not divided by 2, sorry, my memory failed there for a minute. It wasn't divided by 2. Cosine of, not cosine, the sine, this is why I don't trust my memory, sine of gamma b0 t, and the expectation value of Sz that we just found was h bar divided by 2, a squared minus b squared. Okay, so this is what we have right now. Let's try to visualize this, and in order to do that, let's, for example, take a look at some vector that's going to be the expectation value of the spin of Sx in the x direction plus the expectation value of the spin y in the y direction plus the expectation value of Sz in the z direction. So to get an idea of what's going on here, let's sketch this vector that we have just found. Whoops, I didn't select it the way I wanted to. So I'm going to move this up a little bit, maybe put the Sz over here so that I have more space, and this up here. Okay, so let's just make a quick three-dimensional sketch here. Maybe I'm going to try to make an actual straight line. Okay, so this will be the z direction, this will be y, and this will be x. So let's take a look at our vector here. This vector, look at the z component. It's simply this quantity. It doesn't change with time. So this means that the height here is always going to be a squared minus b squared h bar over 2. And so we're always going to be in an xy plane that is at this height in the z direction. So the question is, what's going on in that xy plane? So let's sketch that right here. Make a quick sketch here. So this is going to be y direction, x direction, this is 0, and of course these are the negative directions, and minus x. So let's see what's happening in this plane. So if time is 0, so at the beginning, cosine of 0, this is 1, so we are in the x direction, we are at a, b, h bar, and in the y direction, we are at 0. So that means we are somewhere over here, a, b, h bar, whatever that quantity may be. Then at some later time, let's go for the easy one. So since these are cosine and sine, let's look always for when one is 1 and the other one is 0. That would be, now for example, when cosine is 0. That is when gamma b0 t is equal to pi over 2, or when time is pi over 2 gamma b0. Obviously, which time it is, it doesn't really matter too much, but that's just so that we see. So what happens when cosine is pi over 2? Oh, I mean, the interior here, sorry, is pi over 2. Well, cosine is going to be 0, so we're going to be at x equals 0. But now in the y direction, we're going to be at minus a b h bar, since sine is 1. So we're going to be at minus a b h bar. Now what happens when when the interior here is pi? That means cosine is going to be minus 1, so we get minus a b h bar in the x direction, and y will once again be 0. So we will be here at minus a b h bar. And finally, at 3 pi over 2, we can see that cosine again is once again going to be 0, and sine will be minus 1, so we will be up here, a b h bar. And then the times in between, this is going to be just moving in between. So what is going on here is that we are in a circle. If this doesn't quite convince you, you can just go ahead and use the techniques from calculus to sketch this a bit better. I just want this raw idea. So you can convince yourself that this is actually a circle. You can also see that, of course, because this is parametric in time with cosine and sine, and that is a circle. But however you want to see it, this is indeed a circle. So this means that in this height z, the particle is moving in a circle. This doesn't look like much of a circle, but it is, I promise. So our vector s is always going to lie in that circle. So this is our vector, that this expectation value of s vector. And we can see that this vector is always going to be at some angle that we might call alpha, for example, or whatever you want to call it. This is at some angle with respect to this z direction. Okay, so that seems quite interesting. So maybe let's take a look at some of the results that we have found and see what we can find out about this angle and if it maybe relates to some of the constants that we have used to describe this. So using this sketch, we can actually see that this is going to be a right triangle, of course, with side AB, with the radius ABH bar of the circle, which is going to be this opposite side, and the adjacent side to the angle, well, that's simply the height with it, which is h bar a squared minus b squared divided by 2. So we can use this, in fact, to write the cosine and sine of this angle, and tangent if you want. So the cosine of the angle, it's going to be the adjacent side, which is h bar over 2 a squared minus b squared divided by the hypotenuse. But what is the hypotenuse? It's this side right here, which we don't quite know. So let's call it hypotenuse here. And let's calculate. So the hypotenuse, because of Pythagoras' theorem, this is going to be each one of the two sides squared, and then we take the square root of all of that. And the other side is a squared b squared h bar squared. So let's calculate this. So this first part here is h bar squared divided by 4, a squared minus a to the 4th power minus 2a squared b squared plus b to the 4th power plus 4a squared b squared h bar squared divided by 4. Here I took the common denominator already because I want to put everything together here. Because take a look at this. We have minus 2a squared b squared here and plus 4a squared b squared and this h bar squared that is also multiplying all of this. So let's factor out an h bar squared here and take it outside of the square root. So we get h bar squared square root, and then we have, and in fact we can actually take the divided by 2 as well. So we get a to the 4th power plus 2a squared b squared plus b to the 4th power. But this is simply a squared plus b squared squared. So when we take its square root, we are going to be left with h bar divided by 2, a squared plus b squared. And what is a squared plus b squared? This is simply 1. So this is h bar over 2, because this a and b came for the first time when we were taking a look at this general spin state, which was a times the up state, b times the down state. And since these are the only two possibilities, then the probability of finding it in these two states has to be 1, since they are the only possibilities. That's why a squared plus b squared was 1. So that means that the hypotenuse is h bar over 2. So let's write it in here. So this is h bar over 2, which cancels out this one. So we get a squared minus b squared. And then we have cosine, we already did cosine. Now it's time for sine. So we have sine of alpha, which is going to be the opposite side, which, remember from our drawing, the opposite side is AB h bar. So we get AB h bar divided by h bar divided by 2. So this is going to be the h bar cancel out and the 2 goes up. So we get 2ab. Now, this is a system of equations which we can solve to find a and b. However, doing it is not easy at all. So there is a, maybe, I don't know if I can call it a trick, but there is something we can notice, because this right here and this right here might look familiar if we take a look at the cosine and sine to the left side of these equations. So just to give you a help before I show you, if we have the cosine of 2 theta, how do we write this? We can write it as cosine squared of theta minus sine squared of theta. And in the case of the sine of 2 theta, we can write it as 2 times the sine of theta cosine of theta. And see that this is very similar to what we have up here. We have cosine, cosine, something squared, minus something squared. And here we have the sine, and it's 2 times one something and the other something, right? It looks very familiar. So if we say that A is the cosine of half of alpha, and that B is the sine of half of alpha, then we can see that these equations indeed hold, because cosine squared minus sine squared, that's cosine of 2 times this angle, but 2 times this angle is simply alpha. So with this, we actually found our constants A and B, which is, of course, something very useful. So now we have seen then that the expectation values that we found before, this is not simply AB h bar cosine of all of this. This is going to be, well, maybe I'll take it to a new page so that we can rewrite it. So then the expectation value, maybe I'll change the color to the expectation value of Sx. This is going to be cosine of alpha divided by 2 sine of alpha divided by 2 cosine of gamma b0 t. But here we have cosine sine, and remember, sine of theta of 2 theta is 2 times sine theta cosine theta. So in fact, we can rewrite this part as 1/2 times, right, of sine of 2 times the angle that is in here, but since it is alpha divided by 2, it's simply going to be alpha. So we get sine of alpha divided by 2, by the way, I forgot the h bar here, times h bar times cosine of gamma b0 t. So this is another way in which we can write this, just in terms of this angle that we found. And in the case for Sy, it's actually going to be the same, but with a minus sign. So we're going to get minus sine of alpha h bar over 2, that does not look like an h, and times the sine of gamma b0 t. So now we see that both of these expectation values depend on this angle. So let's just go back one more time and take a look at what this means. So what this means is that this expectation value of this total spin of that direction is going to be precessing around the z direction. So that's going to be constantly changing, and that is why this phenomenon is called the Larmor precession. And we can see, of course, the frequency with which this occurs, because as we have seen, hopefully, or you have seen in your courses in wave mechanics, if we have these cosine and sine, and maybe even in mathematics actually, the frequency is what goes with the time in here. So if you have cosine of omega t, the omega is the frequency. So in this case, we can define what is called the Larmor frequency, because this is the Larmor precession. So the frequency of the Larmor precession is the Larmor frequency, which is gamma times b0. Now, this is something very, very important for experimental physicists, because this has many applications, as I said, in spectroscopy and radioscopy, and there's many things. I think in medical physics, there's also a few applications in medical imaging. So this is very, very interesting for many physicists. So I thought it was good to explain where this phenomenon comes from. So this is going to be it for this video. I hope you enjoyed it, and I will see you in the next one.